Hello, I'm working through the first two problems on page 14 of your guided notes. Working through the graphing problem. What I'm going to do is I'm going to use a combination of writing out what I have without the calculator, then I'm going to use the calculator as a support mechanism. So whatever I see in the calculator, I will immediately understand what it is and why it is. So the first thing here is I'm going to get a list of, obviously we're going to need our vertical asymptotes, horizontal asymptote, or slant asymptote, our X and Y intercepts. Critical points are all a part of this. All of that. But I'm going to start off with my critical points. Critical points from our numerator, critical points from our denominator. The critical points help us get the ball rolling, break the inertia. Also reminding you that the critical points from the numerator tend to become x-intercepts. The critical points from the denominator tend to become vertical asymptotes. If there's an alignment, then it becomes a whole. But be very careful. Again, you cannot just jump to conclusions. If we're taking a limit, that's one thing, but we're not taking limits. We're simply looking for critical points. So looking at the numerator, I have a critical point at 0, giving it time to focus. I have a critical point at 0, at -2, and at +3. I'm also taking note that the degree of the numerator is 4. 1, 2, 3, 4. The critical points of the denominator looks a bit dubious. I will take a moment to remind myself that the degree is 2. So regarding whether or not it's a slant or a horizontal asymptote, we know it's a slant asymptote because the degree of the numerator is bigger than the degree of the denominator. We can't simply set this equal to 0 and automatically immediately know what those answers are. Or if I just wrote down plus or minus I, it might cause issues. So let's set this equal to 0 and solve step by step. We're going to take the square root of both sides. X equals plus or minus the square root of -1. So x equals plus or minus I. So the critical points here are plus and minus I. Those are imaginary numbers. Those are not real numbers. Therefore, there are no vertical asymptotes. And if we actually look at the equation x squared plus 1, there's no way we can get x squared plus 1 to equal 0. That's why we have imaginary numbers. When x is -1, -1 squared is +1. +1 plus 1 is 2, not 0. So it's all the more affirmation that there are no vertical asymptotes in this function. But it does look like we have 3 x-intercepts. We have the x-intercepts. Once we get the x-intercepts, I'm going to go ahead and let's just keep track of everything because there's lots of moving parts. So our vertical asymptotes, not applicable. There are no vertical asymptote. Horizontal asymptote. The degrees of the numerator is greater than the degree of the denominator, so it's not applicable. If there isn't a horizontal asymptote, let's check for a slant or an oblique asymptote. And if we sort of dissected this equation using the method of limits, there is a chance that our slant or slash oblique asymptote definitely exists. And please know it doesn't have to be a linear function. If I take the limit as x approaches infinity of this function x squared, x plus 2, x minus 3, x squared plus 1, as x grows towards infinity, this doesn't mean much. These two essentially simplify to 1, and we're left with x plus 2 times x minus 3, which is a quadratic equation. I think this is another reason why they go back and forth, slanted line. Oblique represents a line that's anything other than perpendicular or parallel. So it can represent, it's an oblique line. This is definitely a line that's not perpendicular or parallel. I think that's another reason why they tend towards, why they use oblique as well. And it's definitely possible that our oblique asymptote or the end behavior of our rational function resembles a quadratic equation. This is essentially the shape, overall shape of the rational function. So now that I have an idea that my oblique asymptote or my slant asymptote looks like this, I'm going to use this, highlight this in green just to keep track of. I'll just box it up because it's blurring. I'm going to move on. We have our vertical asymptote, not applicable, horizontal asymptote, not applicable. We have our slant asymptotes. I'm going to write my x-intercepts where it crosses the x-axis. My x-intercepts are 0, 0. And again, I'm simply drawing this from my critical points. I'm simply drawing this from the numerator of the rational function. -2, 0, and +3, 0. Those are my x-intercepts. Let's calculate the y-intercept to see if it's there, even though we can sort of look and tell. Again, the y-intercept is what is y when x is 0. So I'm going to plug in 0 for x and get y out. Y equals 0 squared times 2 times -3. And we know what's going on here. 0 times anything cancels out. So of course, my y-intercept is 0, 0. We have all the pieces to our puzzle. I'm going to begin graphing it, and then I'm going to use my calculator as support, because if you haven't graphed something like this before, it's like, let me just double check to make sure. We have the equation here. You should have page 14 as well in front of you, but I'm going to rewrite it again just in case. Okay. And I'm going to start off by plotting my x and y intercepts. We have an x-intercept here, 3 and 2, 1, 2, 3. Let's throw 4 in there. An x-intercept at -2 and an x-intercept at +3. I could test points, plug in -3, see what I get out. But let's use the calculator. It is a good device. We just don't want to be so dependent on the calculator that if it leads us astray, we don't even know it led us astray. We're going to have to use lots of parentheses, wrap the entire numerator in parentheses. So it's going to be parentheses, x squared, parentheses, x plus 2, and parentheses, x minus 3, and parentheses again. That is the entire numerator. Division bar, new parentheses for the denominator, x squared plus 1, in parentheses. Okay, let's hit graph and see what we get. And again, we're not completely shocked. We know that there's some sort of a slant asymptote that will make or bend or shape the entire function, or essentially the function tends to look like this function, takes after this function. Noticing here, we also verifies that our x-intercepts are at -2, 0, and 3. So just looking at this, I'm going to go ahead and draw this up. We have this. We don't need to know exactly how far down it goes. That's our function. That's the graph of our function. We know why it looks like this. And again, just showing you regarding the horizontal asymptote. The horizontal asymptote has, I'm sorry, shame on me. This is not a horizontal asymptote because it's not a horizontal line. This is a slant asymptote or an oblique asymptote. The oblique asymptote shares 2 of the same x-intercepts. And then whatever's going on, it's going to look like this quadratic equation. So again, in the short term, it looks crazy or whatever. But as x increases towards infinity in both directions, it takes on the shape of this quadratic equation. And that's the graph of this function. You can label this. I'm going to do short SA for slant asymptote. Y equals x plus 2 times x minus 3. You can label your x-intercepts, but it's obvious because we see it go through the graph. And again, the green line's just there in spirit. It's not really there. That's the equation of the first graph or the first prompt from page 14 of your guided notes. I'm going to now walk through this one. And I'm going to do a very similar approach. There's lots of moving parts. So I'm going to gather all of my moving parts and then put it together and see what I have. So we're told, first off, we're told always use the lowest possible multiplicity. We're told the function has a bounce point at bounce 0 or a bounce point at 3. Fancy way of saying you have an x-intercept where it hits the x-axis and bounces up. So if we have a bounce point at 3, that means the factored form is x minus 3 equals 0. In order for it to be a bounce point, it has to be raised to an even power. So I'm going to throw a 2 there because it did say the lowest possible multiplicity. So that's why I raised it to the second power instead of the fourth power. Next, a pass-through 0 at 2. So x equals at negative 2. So x equals negative 2. X plus 2 equals 0. Pass through. So it's just raised to the first power. It's raised to an odd power. Vertical asymptote at x equals negative 6. That means it's x plus 6 equals 0. But in order to be a vertical asymptote, it has to be in the denominator. So it's going to be x plus 6 down here in the denominator. In parentheses, it says with both parts of the graph heading from the same infinity. From the same infinity. They're not mentioning end behavior. They're not mentioning slant asymptotes. When they say the same infinity, let's say this is negative 6. The same infinity means that it looks like that. They're both reaching towards the sky next to each other. They're even Stevens. If you recall from an exploration at the beginning of the unit, when we dealt with the parent function 1 over x, the vertical asymptote is raised to the odd power. So they are at odds. So that's why it looks like that. When it's raised to an even power, they are even Stevens. So in order to make that work, I'm going to throw a 2 there. Even Stevens, they're on the same playing field. If this is raised to the odd power, they're at odds. For verification, I'm going to go to my calculator, and I'm going to do 1 divided by parentheses x plus 6. We're going to look at that graph. They're at odds. Now let's see what happens when I square that. It's easier just to start from scratch. Squaring it. Now let's see. Now they're even Stevens. So again, a reminder of if the factor used to create your vertical asymptote is raised to an even power on the same playing field, if it's raised to an odd power, they're at odds. Also, picking up where we left off, the y-axis is a vertical asymptote. So the y-axis is a vertical asymptote. We have another vertical asymptote, xy. So that just means it's a vertical asymptote at 0, just like the parent function. So there's going to be an x somewhere in the denominator as well. There is a horizontal asymptote at y equals 2. So the horizontal asymptote at y equals 2. If it's a horizontal asymptote other than 0, that essentially means it's 2 times in the numerator, it's the same degree as the degree in the denominator. Same degree in the numerator, same degree in the denominator. Well, all that's left once we take the limit is 2. So what I'm going to do now is I'm going to take all these moving parts and I'm going to combine them into one equation. Okay. We have an x-intercept here, so I'm going to have, well, let's just do f of x equals, I'm going to have x minus 3 squared, check, times x plus 2. Vertical asymptote, so in the denominator, we have x plus 6 squared. We also have an x down here. And I'm going to throw a 2 here. And now I'm going to see if I add them all up, does it work out? First off, same degree. In order to have the horizontal asymptote, the degree of the numerator has to be the same as the degree of the denominator. 1, 2, 3, check. 1, 2, 3, check. The horizontal asymptote will be 2. Vertical asymptote at 0. Vertical asymptote at -6, where they both reach towards the sky. X-intercept that's passed through at -2. Bounce point x-intercept at +3. Check, check, check. All right, that's it. That's the equation that satisfies this. Let's graph this in the calculator. And this will be a good opportunity to see that, yes, graph in the calculator, but you don't want to be completely reliant or dependent on that calculator. You have to wrap this heavily up, bundle this up in parentheses. So it's 2 parentheses x minus 3 squared, parentheses x plus 2, in parentheses divided by parentheses x, parentheses x plus 6, in parentheses squared, in parentheses, graph. Let's look and see what we get. And let's look at this. We definitely have something going on. When x is -2, we have an x-intercept. When x is +3, you can tell it hits the x-axis when x is +3. This graph doesn't look like, if you simply graph this, you may not be as capable of simply looking at this and drawing this from it. That's why you need to know what's going on and why to make sense out of this. Definitely x-intercept at -2, and it's a pass-through. X-intercept at +3, and it looks like it hits it and bounces up. It just doesn't bounce up as much as we're used to seeing, but we know it rises up. Also, considering that the horizontal asymptote is 2, it looks like eventually it's going to rise up and eventually want to approach 2 as x increases towards infinity. We have a vertical asymptote at 0. We should have a vertical asymptote here. We know what it looks like because we did it by hand. Let's zoom out. And now we see our vertical asymptote. So again, the calculator will only give you a piece of it. That's why it's important to be able to break it down and know what's really going on. So you know that, yeah, that vertical asymptote is here. It was just way out here. And there you go. You've graphed it. In the calculator, you know why it is, what's going on, all of that good stuff. That's it for page 14. Have a good day.